50 years have passed since the Apollo landings, and in all that time, the most vital thing on the moon remains invisible. Why? Despite relentless scrutiny, despite the billion-dollar investments, the moon still guards its simplest secrets. Chief among them, water. How much water is truly there? Where does it hide? On the surface, just beneath, or locked away in the deepest shadows? And perhaps most crucial of all, will we ever be able to claim it for ourselves? For more than 2 decades, the possibility of lunar water was left unexamined. The dogma of a barren, waterless moon became so accepted that any evidence to the contrary was quietly ignored. No new experiments were designed to pursue the question. No missions were planned to dig deeper. For many, the question was closed, and the moon's dryness became a scientific fact, unchallenged and unquestioned. The earliest whispers of water on the moon were almost a scientific embarrassment, dismissed as contaminated samples, leaky rockets, or the meddling breath of Earth's own atmosphere. During the very first lunar landings, when astronauts brought back moon rocks and dust, analysts found faint traces of hydrogen and water molecules. Yet every time, the answer was the same: contamination. The prevailing wisdom was that the moon was bone dry. The textbooks declared it so. The scientists concurred. The idea that the moon might harbor water was so radical, so unexpected, that early findings were quietly tucked away, buried in reports, or left as mere footnotes in the rush to more glamorous discoveries.
For more than 5 decades, humanity has been waging a determined campaign of discovery against our nearest neighbor in space. Mission after mission, American, Soviet, Japanese, Indian, Chinese, and European have journeyed to the lunar surface. Orbiters have circled endlessly, mapping every contour and shadow. Landers have touched down, sometimes with astronauts, sometimes as robotic pioneers. Sample return crafts have dug into the regolith and carried precious dust and rock back to Earth. Some missions have even ended in deliberate crashes, sacrificing themselves to kick up hidden secrets from beneath the surface. In all, we have amassed mountains of data, filled libraries with lunar research, and yet the moon's greatest secret remains as elusive as ever. As new orbital missions circled the moon, they scanned these shadowed regions in unprecedented detail. Advanced radar and neutron spectrometers began picking up something odd: signatures of hydrogen emerging from the PSRs. It was not definitive proof, but it was more than a hint. The prospect of lunar ice went from dismissed theory to a tantalizing possibility. But as so often happens in science, the truth refused to stay buried. A new generation of scientists began to reconsider old data and dream up new ways to probe the moon. They turned their attention to the lunar poles, regions so cold and dark that sunlight never touches them. These are the so-called permanently shadowed regions, or PSRs. Some of these craters have not seen daylight in billions of years. Temperatures in these frigid traps can drop well below -240 degrees Celsius, colder than Pluto's surface. The rationale was simple. If water ever arrived at the moon, delivered by comets, asteroids, or the solar wind, these frozen shadows could preserve it for eternity. This was not just idle curiosity. The implications were enormous. If water existed on the moon, it could be the key to affordable spaceflight, sustainable lunar settlements, and the next era of human exploration. Water could be split into hydrogen and oxygen, creating rocket fuel on site. It could support agriculture, recycling, and life support systems. In short, lunar water would be the foundation for a permanent human presence beyond Earth. How did this riddle begin? And why, after half a century, are we still grasping at shadows and chasing rumors across the lunar surface? Yet, with every new mission, the mystery only deepened. The moon revealed itself as more complex than anyone had imagined. Water signals appeared where logic said they should not, then vanished when researchers tried to get close. The deepest shadows at the poles teased scientists with the promise of trapped ice, but every probe and scan only multiplied the questions.
It was as if the moon were protecting its greatest resource, hiding it beneath a gossamer layer of dust, always just out of reach. The stakes could hardly be higher. If we misinterpret the clues or accept convenient certainties, we risk missing the moon's most precious asset. Tens of billions of dollars, decades of hard-won progress, and global leadership all hang on whether or not we can solve this riddle. The quest for lunar water could make or break entire national strategies and determine which countries or companies lead the next wave of space exploration. To answer, we must go back to the first ambiguous clues: strange signals, muddled samples, and one of science's oldest doubts. Is what we see real, or is it an artifact of our own errors? What if the most vital evidence for lunar water was always right before our eyes, dismissed for generations as an error, a footnote in the rush to other discoveries? But history is full of examples where easy answers turn out to be wrong. Think of the first reports of meteorites containing organic molecules. For decades, scientists insisted those molecules were the result of earthly contamination until better techniques proved they were native to space. Or consider the early hints of life on the ocean floor, dismissed for years only to be confirmed with new technology. The moon's water is just the latest in a long line of scientific mysteries where dogma delayed discovery. For over 20 years, this belief went unchallenged. The idea of a barren, waterless moon became so accepted that early hints were quietly shelved, left to fade in forgotten laboratory drawers. No one chased the signals. No one designed new experiments to dig deeper, either in theory or in lunar soil. The possibility that the moon might secretly harbor water was simply left behind. When the Apollo astronauts returned with samples showing trace amounts of water or hydrogen, the explanation was always the same: contamination. It was the easy answer. During the age of Apollo and Soviet Luna missions, scientists found faint chemical clues in moon samples. Astronauts brought back dust and rocks. Robotic probes, such as Luna 24, drilled beneath the surface, returning precious cores. Within these samples lingered tiny yet unmistakable traces: minute amounts of water, molecules of hydrogen, and telltale hydroxyl groups. Each time, the answer was the same: contamination. The water must have come from Earth, or perhaps from leaky equipment. The textbooks declared the moon bone dry. That was the truth everyone believed. The moon, it turned out, still guarded its secrets. In the 1990s and early 2000s, as new missions with sharper instruments arrived, scientists began to pay attention to the lunar poles. Here, in the PSRs, they found conditions unlike anywhere else in the solar system. These craters, untouched by sunlight for billions of years, could act as natural cold traps. Any water that drifted in, delivered by comets, meteorites, or chemical reactions, could freeze and remain preserved, protected from the harsh lunar day. Still, scientists remained cautious. Numbers on a screen are not proof. The signals could be caused by hydrogen in other forms, or by unusual soil chemistry. We needed to see it for ourselves. This realization was not theoretical. Earth itself contains cold traps in the form of permanently shadowed caves and deep polar valleys where water ice can persist for millennia. On Mercury, a planet even closer to the Sun than Earth, scientists also detected water ice in permanently shadowed craters. If Mercury's poles can trap water, why not our own moon? As more advanced orbiters mapped the moon, they detected hydrogen signatures, particularly near the poles. The data was suggestive. Perhaps hundreds of millions of tons of water ice could be locked beneath the ancient dust. This was a staggering number. To put it in perspective, if even a fraction of that water was accessible, it could supply generations of astronauts, fuel fleets of spacecraft, and support entire lunar settlements. That is why, in the early 2000s, NASA and other space agencies began a new approach: active exploration. The Lunar Prospector mission, for example, tried to force the issue by crashing into the moon and watching for water thrown up in the blast. Each time, the silence was deafening. No icy plume, no telltale vapor, just more questions. The moon, it seemed, was not giving up its secrets easily.
Then came the Elsie Cross mission in 2009. NASA sent this probe on a kamikaze dive into a crater cloaked in eternal darkness. Instruments on Earth and in orbit watched the impact, hungry for clues. This time, the gamble paid off, at least partly. The plume contained water vapor. Finally, proof. The moon was not completely dry after all.
Yet the triumph was fleeting. L-Cross showed water was present, but not how much or how it was stored. Was it a thick, mineable sheet of ice, or just wisps tangled in dust? Was it close enough to reach, or buried deep beyond any hope of extraction? The answers vanished back into the shadows. Meanwhile, the mystery deepened. New orbiters picked up traces of water and hydroxyl, not just in the frozen poles, but even on sunlit ground. The signals shifted with the temperature, as if the moon itself was exhaling moisture. But how? The moon has no air, no weather, no water cycle, none of the tools Earth uses to move water around. Desperate for answers, scientists spun new theories. Maybe tiny meteorites deliver water, molecule by molecule, every time they strike the surface. Maybe the solar wind stirs up chemical reactions, building water out of lunar minerals grain by grain. Each explanation seemed incomplete. The more we learned, the more elusive the truth became. Lunar water was everywhere and nowhere, both abundant and impossibly scarce.
In this fog of uncertainty, every mission, every dollar invested in lunar exploration is a leap into the unknown. Without real answers, nations and companies are wagering their futures on what amounts to an educated guess. The stakes have never been higher.
Yet the search for answers continues. Cracking the enigma of lunar water could rewrite the future of exploration and reshape the power balance beyond Earth. Recent discoveries have only sharpened the dilemma. Water might exist across the moon, but mostly as fragile films, thin as a few molecules, or buried deep beneath layers of rock. If so, dreams of mining vast reserves could be just that, dreams. The cost of being wrong is staggering. Entire national strategies, multi-trillion-dollar industries, and visions of lunar colonies could hinge on a secret hidden in the shadows. What happens when hard evidence on the ground clashes with decades of promising signals from orbit? But when the Pragyan rover began its careful survey, it found nothing. No sign of hydrogen, no water to speak of. The signals from space, so clear for so long, seem to have led us astray.
Consider India's Chandrayaan-3, which sent its lander closer to the lunar South Pole than any previous mission. This region is the moon's best hope for ice, a potential treasure trove for explorers. For years, satellite observations had pointed to water, giving hope that the surface would finally reveal its secrets.
This discovery raises a tantalizing possibility. Water might exist, hidden just out of reach. The Apollo missions found more water in deeper samples. The Soviet Luna 24 mission drilled down and recovered its highest concentrations from beneath the surface. Perhaps the moon's water is not gone, only buried, locked away beneath dust, shielded from sunlight and our shallowest tools.
Instead, Pragyan uncovered something else. Its sensors detected sodium in the dust, an unexpected result. Even more surprising, thermal readings showed a dramatic drop in temperature just beneath the sunlit surface, plunging from about 50 degrees Celsius to nearly minus 10 degrees in shaded regolith only a few centimeters down. The moon's thin crust acts as a powerful insulator, trapping cold and concealing whatever may lie deeper below.
Yet the mystery only grows. NASA's shadow cam peers into the eternally dark craters with unmatched sensitivity, but still has not found clear, gleaming sheets of ice. Radar and neutron detectors keep picking up signals that suggest water, but the data is muddled, sometimes contradicting, sometimes reinforcing older hopes. So where is the water really hiding?
Some scientists believe it is trapped as molecules fused to minerals, bound tight within the lunar soil. Others argue it is buried deeper, preserved by layers of undisturbed dust over centuries. And some worry that the tantalizing orbital signals are illusions, traces of hydrogen that do not add up to usable water at all. So if the water exists, why does it elude us? If it does not, why do our best instruments keep hinting otherwise? Every new probe and every new reading only deepen the puzzle, sharpening the stakes for the spacefaring nations vying to solve it first. The search is more urgent than ever as the next wave of missions prepares to dig deeper and risk more. Whoever finds the truth about lunar water first could reshape humanity's future in space. Lunar water is no longer just a scientific curiosity. It is quickly becoming the linchpin of true independence in space. This uncertainty is far more than academic. The very future of lunar exploration and humanity's foothold beyond Earth may depend on the answer. If there is no accessible water, plans for moon bases, rocket fuel, and deep space travel could unravel. The moon, imagined as a gateway for human expansion, might remain off-limits, simply because we cannot unlock its hidden reserves. The moon's weak gravity offers a natural launchpad for the solar system. It takes much less energy to escape the moon's pull than Earth's, especially if fuel is available on site. The result? Massive interplanetary missions become drastically cheaper and more scalable than ever before. If we can unlock water on the moon, everything changes. No longer would we be forced to launch every single drop from Earth at staggering cost. Local water could save untold millions, making reliable life support systems for astronauts not only possible, but also practical. Drinking water, breathable air, and even simple showers, all from lunar resources, would break our dependency on fragile supply lines stretching across space. But the true revolution is this: water equals rocket fuel. Split water into hydrogen and oxygen, and you have the very propellants that launch rockets today. If lunar water can be mined and refined, future crews could refuel right on the moon. Suddenly, Mars missions, asteroid mining, and journeys into deep space could all launch from a lunar base, powered by resources mined underfoot. Water is also the heart of agriculture and recycling, essentials for any permanent moon base. Crops need water to grow, waste needs water for recycling, and closed-loop life support systems rely entirely on a steady local source. With dependable water, a lunar outpost stops being an expensive camping trip and starts becoming a thriving frontier settlement. Imagine a future where astronauts land at a moon base and are greeted with fresh vegetables grown in hydroponic tunnels, all fed by water mined just meters away. Where oxygen for breathing is extracted from lunar water, and excess hydrogen fuels rockets heading deeper into the solar system. Where recycling systems modeled after Earth's most advanced ecologies keep every drop in circulation. Such a vision depends entirely on unlocking lunar water. But here is the catch. Every bold plan and race depends on a single, stubborn question. No one has yet confirmed exactly how much water is there, how pure it is, or how difficult it will be to extract. Whoever solves the moon's water riddle first will set the rules for all who follow. Fall behind now, and there may be no coming back. This is much more than a scientific challenge. It is a new geopolitical rivalry. The moon's water is the key to lasting presence, influence, and even security in space. Miss this opportunity, and a nation risks losing its place in the coming era of exploration. Billions of dollars, decades of technological leadership, and the very future of off-Earth civilization now hang in the balance. With so much at stake, what is the next step in the search? And can we finally break through the lunar silence? Yet the stakes reach far beyond survival. They shape the balance of global power. Control of lunar water means control over who can live, work, and travel in space. Whoever secures these icy reserves will set the terms, dictate prices, and steer the logistics of every future mission. It is no surprise that the world's leading space nations are racing to the moon's most promising sites, especially the shadowed craters near the South Pole, where frozen water may wait in eternal darkness. The answers may lie in a new generation of missions, each daring to explore the moon's darkest and most mysterious corners. But first, we must confront the daunting challenges that have kept these secrets hidden for so long. What if the real breakthrough is just one drill deeper? For all our missions, all our footprints and flags, the moon's greatest secret might be hidden beneath a layer no thicker than your finger. Decades of exploration have merely brushed the surface, yet the true mystery, water, the bedrock for life and industry, could be sitting only centimeters below, untouched and unseen. This is not just science. The stakes are colossal. Unlocking the moon's water could slash the cost of reaching Mars, make permanent lunar bases possible, and rewrite the balance of power on Earth. The next mission could launch a new age for humanity, or reveal how fiercely the universe guards its secrets. Every probe, every rover, and each byte of data has led us to this edge. But sometimes, discovery demands we question our methods, challenge what we believe, and dig just a bit deeper, both physically and scientifically. Every centimeter excavated might bring us closer to the turning point that could remake the future of space exploration. Now the story shifts. The world's strongest nations, daring private ventures, and the sharpest minds are ready to go further than ever before. This time, they aim not just to scratch the surface, but to pierce through the unknown, knowing that what they find could determine who leads humanity's next giant leap. The quest to find water on the moon is not merely a technical challenge. It is a test of human ingenuity, patience, and resilience. So let us look at some practical steps and scenarios that could finally tip the balance in our favor. Will the next drill strike water, or will we be forced to start over once again? The moon has guarded its secrets for billions of years. Today, we stand closer than ever to cracking them, but only if we are bold enough to dig beyond every limit we have set. First, future lunar missions must go beyond surface surveys. We need to send specialized drilling rovers capable of penetrating several meters into the regolith. Imagine a fleet of robotic miners, each equipped with ground-penetrating radar, neutron detectors, and sophisticated spectrometers. These machines would not only dig, but also analyze samples in real time, mapping the distribution and form of water as they go. Second, international cooperation and data sharing will be vital. Countries like the United States, China, India, Russia, and members of the European Space Agency each bring unique technologies and expertise. Joint missions, open access databases, and coordinated exploration strategies could prevent duplication of effort and accelerate breakthroughs. Third, we must develop in situ resource utilization, ISRU, tailored for the moon's harsh environment. This means building plants that can extract water from lunar soil, purify it, and split it into hydrogen and oxygen using solar or nuclear power. Such facilities will need to be robust, automated, and capable of operating in extreme cold and darkness. Prototypes should be tested on Earth in lunar analog environments, such as the Antarctic dry valleys or volcanic deserts. Historical parallels remind us that transformative discoveries often follow decades of false starts and skepticism. When explorers first searched for gold in the American West, many initial expeditions returned empty-handed. Only after years of persistence, new techniques, and better understanding of geology did the great gold rushes begin. The hunt for lunar water may be following a similar arc: frustration, incremental progress, and then, perhaps, a sudden breakthrough. In the meantime, we must be ready for disappointment. It is possible that much of the moon's water is bound tightly to minerals, requiring energy-intensive processes to extract, or that accessible ice only exists in scattered pockets, making large-scale mining impractical.
However, even small amounts could be game-changing for early outposts, providing proof of concept for more ambitious endeavors. Consider a scenario: a multinational team lands at the rim of Shackleton Crater, the most promising site for lunar ice. Their rover drills down, meter by meter, and at last hits a layer of frost. Sensors confirm the presence of water molecules, not just hydrogen. Teams on Earth erupt in celebration. The outpost is resupplied with local water. Future missions plan to expand mining operations. A new era of lunar industry is born. Regardless of the outcome, the pursuit itself will push technology, science, and international cooperation to new heights. Each step brings us closer to understanding not only the moon, but our own potential as a species. Alternatively, imagine the opposite: years of drilling, but only trace amounts are found, too little to sustain a base. Engineers pivot, developing ultra-efficient recycling systems, and focus on extracting oxygen from lunar rocks instead. The dream of a water-rich moon is deferred, but not destroyed. In closing, the moon's water remains one of the greatest scientific and practical mysteries of our age, a secret locked away in shadows, dust, and stone. The evidence is tantalizing, the stakes are immense, and the race to solve it is heating up. Whether the answer proves abundant or elusive, the journey to find it will shape the destiny of exploration for generations to come. And so, the question remains: will the next probe finally crack the code, or will the moon keep its secret for another 50 years? The world is watching, the countdown has begun, and the future of space, perhaps of civilization itself, hangs on what we find in the cold, silent dark.